Hello everyone and welcome to another tutorial on the channel. Today we're talking about three techniques to solve DC circuits. Previously we've discussed two techniques, which are the nodal analysis and mesh analysis, but today we're discussing another three techniques. So totally we will have five techniques to solve DC circuits, which are you can also use them to solve AC circuits later on, but in this moment, five techniques in your pocket to solve circuits. It's very good. So today we're discussing the current divider rule and of course his brother, the voltage divider rule, and the last one, which is the source transformation. So a lot of you might ask me why I just put all these three together, because first of all, because voltage divider rule and current divider rule are almost the same, so they have to stick together, okay? And about the source transformation, I just put it here together because I feel like it's easy, and also because source transformation is related to them, okay? So and I want you to get the whole picture. When you get a whole picture of something, it will be easier for you to understand it instead of taking small pictures separately. And that's my opinion. So if you are here to just watch the voltage divider rule and current divider rule, you can stop at that point. So you don't have to watch the source transformation. So without further ado, let's get into the video. So before I start, I have to talk about something really important, okay? And let's talk about the parallel elements and series elements. So let's start with the series elements. The series elements in a circuit, they are common in one thing, which is the current. The current passing. So let's give an example. Of course, some of you know the capacitor and inductors. So let's draw a basic circuit. For example, here I have a resistor, and here I have an inductor, and here I have a capacitor. It's a very simple circuit. This circuit has same current, passes through all these three elements. Here Ix, for example, and here is also Ix, and here is also Ix, and it passes in the same direction. So Ix here is going to the right, and this Ix, it cannot go left. This is impossible, okay? So it's like, imagine it is a pipe and there is water inside. If the water passes from here to here, so here, of course, it's going from left to right, and still goes here, and the current passes in the same direction. When I want to say that the elements in series has the same current, uh, there is something might confuse some of you, which is the junctions or nodes. So if you have a circuit like this, here is also like resistor, and here let's say a capacitor. The current passes in these two elements, this one and this one, is not the same. Why? Because these two elements are not series. Okay, this is very important. These two elements are parallel. Since here is no current source or voltage source, so we can say that these two elements are parallel. So let's put, let's say here is a voltage source. Okay. So now these two elements are not in parallel nor series. Okay, so they are in something between series and parallel. So I cannot say that these two sources have the same current. I cannot say that these two, I'm sorry, excuse me, not sources, these two elements, resistors. I cannot say that these two resistors has the same voltage nor current, okay? They are not related to each other at all. So in case of junctions, the current that passes from negative to positive here will, let's say that will divide into two ways. One is here and one is here. So that's why we use the not KVL, what we call it, the KCL, Kirchhoff current law, in this junction to determine the currents, okay? So in case of junctions, this idea is not applicable, okay? We are talking about series, pure series elements, like in this circuit. So in series elements, it has the same same current. And in parallel elements, the elements has, let's draw a circle. For example, here is a resistor, here is an inductor, and here is a capacitor. These three elements are in parallel. So when elements are in parallel, that means they are shared the same voltage. And here same current, and here same voltage. This is very important. So let's say that the voltage here is Vx. Here's the positive, here's the negative. And just like here in the current, we cared about the direction. We said from left to right, and here it must be from left to right, right? So here is also, I care about the negative and positive signs. The negative is down and the positive is up. Since these two elements are in parallel, definitely the voltage here will be Vx, and here will be the positive, and here will be the negative. Same as this one, without any confusion. And the third one is also Vx, and here is the positive and here is the negative. So in the voltage, the amount and direction is same in parallel elements. And for the current, the amount and direction is same in series elements. Okay, so let's pay a super extra focus in these two words. Okay, that in the if I want to have same voltage, let's not say it like this way. When you have a parallel elements, okay, when you have parallel elements, that means all elements has the same voltage and the same direction. When I say direction for voltage, I mean that the negative and positive sign, okay? And here I will discuss something later on, but not now. I will back to this page when I talk about source transformation, okay? But for now, let's go directly to the voltage divider rule. Voltage divider rule, it's a rule, so you can memorize it as it is here. And I will explain these letters, or you can understand it, but I recommend you to understand it so you're able to solve as much as problems as you want. So now let's give an example. If I have a voltage source here, let's say it's 5 volts, and I here have a resistor, and also here I have a resistor. Let's say that this one is 2 ohm, this one is 1000 ohm. Will you see how difference between these two resistors, right? One is big and one is very small. How much voltage in this one and how much voltage in this one? So without any confusion, since these two resistors are in parallel, I can say that these two resistors has the same voltage. Okay, same voltage. And these two resistors are parallel with the voltage source. So all three elements has same voltage. And here I know that this element or this source has a 5 volt. So this one has a 5 volt and this one has 5 volt. Boom. You solve the whole circuit. You see how easy it is? But it starts to be confusing when I put an element here. If you put an element here, the equation will disturb. It will not be direct as it was. First of all, since here is no resistor, that means these two elements are in purely parallel, right? It's directly parallel. So you can take the parallel of them. So if you want to calculate in the calculator, it will give you a number. But for saving time, I will assume that giving them parallel will equal to 50 ohm. This is an assumption, okay? This is not an actual number. But if you just put 2 parallel to 1000, I will assume that the answer equals to 50 to not waste time. So if this one is 50, and here I have a resistor, let's say it's equal to 10 ohm. How much voltage here? How much voltage here? You have two options. First, using voltage divider rule, which is the faster way. The first way, or the basic way, is to find the current that passes through the circuit Then after finding the current, multiply the current by 50. That will give you the voltage at the 50 ohm resistor. But this way it is two-step solution. But while in the voltage divider rule, you will use only one equation. So directly 4 volt. Now I will explain the letters that I put in, okay? First of all, Vx. What is Vx? Vx is that it is the intended voltage that I wish to find. So if I want to find the voltage through the 50 ohm resistor, I will call it Vx. Actually, you can call it anything, but I will use it here as letters so you understand it. Then you do whatever you want. So Vx is the intended voltage to find. Vs is the voltage source. This is Vs. S refers to source. Always when you see me put Is or Vs, that means voltage source and current source. Now let's go for Rx. Since this one is Vx, then the resistor will be Rx directly. This one is Vx, resistor is Rx. Rx is still Rx. Ry is the other resistor that will divide the voltage on. So let me explain one idea before I do this. In voltage and current divider rules, it also has to divide things between two things. You cannot divide the voltage between three things. So let's give it, I will explain it in the current source because it's much easier to understand. So if this is a current source, okay, let's say that this is a current source, and I have three resistors. Here I cannot use the current divider rule. Why? Because these are three. 1, 2, 3. Current divider rule and voltage divider rule are only applicable when you divide the current and the voltage between two elements, 1 and 2 only. In the case when you have three, let's assume that you have a third resistor. If you want to find the current here, you take these two and put them in parallel or in series or whatever orientation they are in. You make them one resistor and make this one resistor. So you have the intended resistor that you wish to find the current or voltage in versus the others. So it's like one versus all, okay? The intended element that you wish to find the resistor, the voltage or current in versus the others, all others. And when I say others, that means that you have to put them in orientation, whether in parallel, series, or any combination, okay? This is the idea. So when you do whatever it is, was a current divider rule or voltage divider rule, you have to put one element, which is the intended one, which I refer it with Rx. I wish to find Vx or I wish to find Ix. This is what I intend to find. These are versus the Y. And here I only have one resistor. That means this is Ry. Okay. In other circuits, for example, you might have a voltage source, and here is resistor, let's say parallel, and here is a resistor, and here is a resistor, and here is a resistor. Here I wish to find this Rx. I wish to find the voltage here. This is Vx. Okay. I wish to find the voltage here. That means this is Vx and this is Rx. And all these, not only this, not only this, and not only this, all three of them together, these are Ry. Okay. So I combine them, whether in series, parallel, any combination I do it. All these three resistors are Ry. Okay. This is the idea. I hope that it's obvious for all of you. If you don't understand it, please tell me in the comments what you don't understand. I am trying to do my best to answer all of you guys. So let's back into this example. Now, let's put it's a mess up, okay? So let's try from the beginning. Vx, I'm sorry. So Vx, the intended voltage that I wish to find. Vs, the voltage source. Rx, the intended resistor. Rx is the same. Ry, the remaining resistors. Or let's say not the remaining resistors, let's say the other resistors that will be divided the voltage on them. Because in some circuits you might do voltage divider rule, and there is some elements, resistors or others, that do not divide in them. Okay. So if this one is 50 and this is 10 and this is 5, substitute all of them in this equation and you will have Vx directly. So now Vx is equal to Vs is equal to 5 multiplied by Rx, which is 50, divided by Rx 50 plus Ry, which is 10. So it is 65 multiplied by 50 over 60, the 0 with the 0, so it is 25 over 6, which is equals almost 4.16, I believe, volts. Okay, so it is straightforward. It's not confusion at all. And if you are not expert, if you just pay a small attention, that you will find that this thing is the unit of this thing is unitless, because ohm over ohm, that means it is unitless. And if you just put it in some organization, if you just put Rx plus Ry under the Vs, Rx plus Ry, that you will find that the Vs over Rx plus Ry, this is S, we will find that this one is the current that passes through the circuit. Isn't that correct? The voltage divided by the sum of the two resistors. Isn't that right? These two multiplied by Rx, the current multiplied by Rx, so you have the voltage through this resistor. But you just don't think about it as this, that you find the current first, then multiply by a current by the resistor. No, just think about it as something that you, like a rule, that you substitute in it and solve it directly. Voltage divider rule, boom, it is easy. Substitute in this formula and believe me, it will be very easy, guys, okay? Now let's move on to the, what we call it, the current divider. Current divider rule is also a formula and solve it. I will not waste a lot of time here because you understand what is the formula. But the only difference is here that Ix is the intended current to find, Rs is the current source, Rx plus Ry, I know them, Rx is the resistor, intended resistor, and Ry is the other resistors, but in the denominator I will put here Ry. Here in the voltage divider I will use to put Rx, but here I used to put Ry. Okay, what is the difference? You will see now an example. So let's say that this is a current source, and here is a resistor, and here is a resistor. Let's say that this one is 3 ohms, this one is 4 ohms, this one is 2 amps. Okay, I said that the current is same in what? In series element, but these two elements are not in series, these are in parallel. So the current will go here and stops in this conjunction, and it will divide here and here. Okay, let's say that here I have a resistor. Is this current that passes from here to here will divide into here and here? So this current, let's say it again. So if I have a resistor here, let's say it's R, let's say it is RV. For example, the current, the 2 amps, is going from here to here and here. It will divide into two ways, here and here, right? Will it divide into here and here and here? No, definitely no, because the current is stuck in this junction. It has nothing to do with this junction, okay? So the current is from here, it will divide into here and here, okay? And these two. So this one has nothing to do. Why I gave you this example? Because I just want to say that if I have this resistor, let's say this one is 10 ohms, and I wish to find Ry, I'm solving for this. Let's solve it and you will understand, okay? So let's go. So the current is here, right? I wish to find this current. If you wish to find this current, that means this one is Ix, and this is Rx, okay? So let's say I X is equal to IS, which is the current source, 2 amps, multiplied by RY. In the denominator, I used to put RY. What is RY in our case? RY, which is the resistor that the other resistor that will divide the current in. So the current will divide into here and here, okay? So this one is the intended one. So this one is Rx. Rx is 3 amps, 3 ohms. So let's put Rx. Now here I wish to find Ry and here Ry. How much is Ry? So if you said that Ry is 4 ohms directly, you are correct. Because the current is only divided into 3 and 4. It will not divide into 10. So 10 has nothing to do with Ry, okay? The 10 has nothing to do with Ry. But if I have a resistor here, let's say that this is the 10 ohms. Here I have to worry about this resistor because the current will divide into here and here and here. So it's a 3. So I will take these two in parallel. I will combine them in parallel. Then the combination of them will give me Ry. I hope what I said now is made them more obvious to you guys to understand. Then you just solve this one mathematically and you will have Ix equals something in amps. That's it for the current divider rule and voltage divider rule. They are very easy. These are the two rules that you need to use to solve these problems. And that's it. But now, if you are here in this video to watch the current divider rule and voltage divider rule, that I think that your job here is done. I hope that you enjoyed the video. But if you're here to also watch the source transformation part, let me tell you this thing before I start, sorry. Now let's back here to the first page. So in series, we add the batteries, we add the voltage sources. In parallel, we add the current sources. Let's give you an example. So this one is a voltage source. Okay. This one is a voltage source. This one is a voltage source. This is 1 volt. This is 1 volt. This is 3 volts. Since these 3 voltage sources are in the same polarity, negative, positive, negative, positive, negative, positive, that means we add these 3 voltage sources. Okay, that means I have here what? I have here 1 plus 1 plus 3, which is 5 volts. So you can just cut, or let's say that you can make a shortcut of this circuit with 5 volts. Now you make the circuit easier. So for convention, I just close the circuit here, but assume that here you have a lot of elements and stuff, okay? But for convention, I just close the circuit earlier, okay? And if you have these these voltage sources with opposite polarities, so let's say here is a voltage source and here is voltage source. This one is negative and this one is positive. This one is positive then negative, okay? So let's say that this one is 5 volts and this one is 2 volts, okay? First of all, that these two, since they are in series, they will merge, okay? But you don't know how they will merge, whether you will sum them or you will subtract them. Here I merged them, but since all these 3 voltage sources are with the same polarity, negative, positive, negative, positive, negative, positive, I added them. But now these 2 voltage sources are in series. Okay, I agree, but they are not in the same polarity. So what you do, you subtract. But you do not subtract directly 5 minus 2 is 3. No, that's a big mistake. First of all, you have to put the voltage source. They will merge into one voltage source. Okay, we agree. Then you will put the polarity of the higher voltage. Which one is higher voltage? This one, of course. 5 is greater than 2. The polarity of the 5 is negative then positive. This is very important. This is very, very important. The polarity of the higher one, which is the 5, is negative then positive. So I put same polarity. Now I go to see that 5 minus 2 equals to 3 volts. You see how this one is tricky? Let's give you another example. If you have here 2 voltage sources, and this one is negative then positive, and this one is negative then positive. This one is 10 volts, and this one is 20 volts. So you will put the merged voltage source. Then you will put the polarity of the higher one. Which one is the higher one? This one is the highest. So you will put positive then negative. Okay. Now you will subtract 20 minus 10, which is 10 volts. But look at the polarity. This one is not the same as this one. These two are not the same. Okay. If you now let's say that here I don't have the 20. If I added this two, what will be the answer? Will it be 20 volts or it will be 0 volts? And if it is 20, is it positive negative or negative positive? Actual answer is 0. It will not be 20 because since these two polarities are different and they are equal in size or equal in magnitude, they will cancel each other. Okay, so now we understand how to add batteries. And if you have batteries in series, in parallel, you cannot add them. Okay, if you have batteries in parallel, you cannot add them. We add batteries only in series. Okay, and same thing with current sources. Current sources are addable when they are parallel. If current sources are series, you cannot add them. Okay, if current sources are in series, you cannot add them. You can add them only if they are parallel. So let's give you an example. If this current source is up and this current source is also up, excuse me, and this one is 2 amps, this one is 1 amp. So it is like that we did a KCL in this node. This node is 2 amps coming here, and in this node we have 1 amp coming here. So the sum that goes to here is 3 amps, right? Since I know, definitely I know 100% that this current is 3 amps, I can make a shortcut by making a new current source that equals to 3 amps passing through whatever was here. So let's say that there are a lot of elements, that these are a lot of elements will be here. This is a simple for shortcut. If you have a lot of elements behind the circuit, you don't have to draw all things. You can just refer to it by symbols, okay? And the same thing if these current sources are in opposite direction. Same thing, you will subtract. But first you have to put the direction of the current source with the higher current. So let's say that here I have a current source with 10 amps, and here I have an opposite current source with 5 amps. And note that these two are what? In parallel with each other. If they are in series, you cannot add them. Since they are in parallel and they are in opposite direction, you will subtract, but first you have to put the direction of the current with the higher, the direction of the current source with higher current, which is this one, it's up. So now you will say 10 minus 5, which is 5 amps. And whatever was here will still remain to be here. Okay, so to sum up, you can add voltage sources if they are in series to each other. And if they are with the same polarity, we add different polarity, we subtract, but we put the polarity of the higher voltage source. And with the current sources, we add them if they are in parallel only. If they are in series, we don't add them. And if they are in opposite direction, we put the current source with the higher current, then we subtract the two current sources. This is an introduction for the source transformation. Source transformation is straightforward as I put here. Source transformation is substituting between a voltage source and a series resistor to a current source with a parallel resistor. And how to change to it using Ohm's law, whether by saying the voltage source is equal to the current source multiplied by the resistor, and or by saying that the current source is equal to the voltage source divided by the resistor, which are same as Ohm's law. And we know that this symbol refers to something called inversible, that I can go into this direction or also I can go to this direction. So you are also can convert from a current source with a parallel resistor to a voltage source with a series resistor. With examples, it will be easier. So let's say that I have a voltage source here, and here is a resistor, and here I have elements, whatever they are, okay? And here is the remaining of the circuit. This one is 5 volts, and this one is what? Let's say this one is 1. No, let's say 2. Let's say 2 ohms, and we'll make this one 6 volts. Okay, so I'm converting between a voltage source and a resistor with series with this voltage source. Let's pay a lot of extra attention to these parts. The series resistor with the voltage source and the parallel resistor with the current source. Since this resistor is series with this voltage source, I can convert them to a current source and a parallel resistor, and then I will put the remaining circuit. Okay, the resistor is the same, always the resistor is same, it will not change, the resistor, so it's 2 ohms. Okay, the resistor will not change. Now let's find the value of the current source. The value of the current source will equal the voltage source divided by the resistor. The voltage source was 6, so 6 divided by the resistor, which is 2, equals to 3 amps. So the current source is equal to 3 amps. You see how simple it is? Now let's give another example. If I have a current source, let's say 2 amps, this is the current source, with a series with a 5 ohm resistor. And here is the remaining of the circuit. Can I use source transformation here? Definitely no, you cannot. Why? Because I said that the current source, it has to be with a parallel resistor. In order to convert it to a voltage source with a series resistor. Now this current source with a series resistor, so I cannot use source transformation. Either this resistor be in parallel, or this current source is a voltage source. So if this resistor is here, is in parallel with the resistor, the resistor is parallel with the current source, I now can use the voltage, not voltage, what we call it, the source transformation, I'm sorry, the source transformation. So now I just use the Ohm's law, the voltage source is equal to the current source multiplied by the resistor. So this is the voltage source, and here is the series resistor. Directly you have to change the parallel resistor to a series resistor, and the series with the voltage source and the parallel resistor with the current source. So here is the 5 ohm. Just like I said, the resistor value will not change. Don't change it, okay? And here will be the remaining of the circuit. And the value of the voltage source from here, voltage source will equal to the current source multiplied by the resistor. The current source, which is 2 amps, multiplied by the resistor, which is 5, so it's equal to 10 volts. So the source transformation is very easy. But source transformation is very tricky when you're trying to deal with bigger circuits. So let's take an example, the final example in this tutorial, which is from our reference book, The Fundamental of Electric Circuit, 5th edition. I always put this reference book in the description down below. So in this circuit, use source transformation to find the value of VO or V naught, which is this voltage. How to find it? You can use nodal analysis. You can use mesh analysis. That's correct. If you use mesh analysis, you will face a super mesh here, because this current source between two meshes. And if you used nodal analysis, you have two nodes, one here and one here. So it is kind of big deal. But let's say if I used source transformation. If I use source transformation, I will note that this current source is parallel with what we call it is parallel with the 4 ohm. So let so in order to convert the current source to a voltage source, I multiply. So this one will be a voltage source. And also, I didn't tell you this, guys. This is very important. If the current source is up like this, I will convert it to a voltage source with the positive sign up and the negative down. So if this is a current source, I will convert it into a voltage source like this. And if I have a current source like this, I will convert it into a voltage source like this. Because we assume that the current passes from the negative to the positive like this, right? And the current is still passing like this. It's just a convention. So if the arrow is up, the positive is up. And if the arrow is down, the positive is down. Okay, I just forgot to tell you this, guys. So, and here we see that the arrow is down, so the voltage source will be down, the negative up and the positive down. And the resistor will be what? Will be in series with the voltage source. The resistor will be equal to 4 ohm. Don't change the value of the resistor. And the value of the voltage source using Ohm's law, 3 multiplied by 4 is equal to 12 volts. 12. And here is the 4. And here we note also this is the 2 ohms. And here is the 8. And here is the 3. And yes, we note that here is a voltage source with a resistor in series. So I can convert them into a current source with a parallel resistor. So this is the parallel resistor, the 3 ohms. Directly, here's the 8 ohms, which is the V naught. And here is the new current source. To note that the positive is up, so the arrow will be up, okay? And the value of the current source, 12 divided by 3, which is 4 amps. And here is the 2 ohms. Okay, I will take these two in series. They will be equal to 6 ohm, one resistor. Now I have a resistor in series with a voltage source. I will convert it to a parallel. So 12 divided by 6, which is 2. And we know that the arrow is down and the positive is down, so the arrow will be down. So this one will be 12 divided by 6, which is 2 amps. And here I have the parallel, the 6 ohms. And here I have also the 8 ohm. And here I have also the 3 ohm. And here I have the arrow up, 4 amp current source. We know that all these three elements are in parallel, so all these three elements has V naught. I will take them in parallel. Let's assume that let's give it an assumption, okay, that the 6 ohms parallel with 8 parallel with 3 will equals to R. Okay, this is an assumption, okay, to save time. Let's assume that all these three in parallel equals to Rx. You can pause the video and calculate it, okay, to find the value, but will do that to save time. So this one is Rx. The circuit will be look like this: an arrow down, and Rx, and arrow up. This one is 4 amp. This is Rx, and this one is 2 amps. We know that these two current sources are in parallel and the directions are different. So what you do is straightforward, put the arrow of the higher current source. Which one is the highest current source? This one. And the arrow of it is up. So and then subtract 4 minus 2, which is 2 amps. Okay. Now you put back Rx. And as I said, that Rx, since all these three are in parallel, all these three will have not Vx, which is V naught that he gave in the question. And here will be V naught. Okay, and let's if you want to call it Rx or R naught, you can do it in either ways. It is correct. Okay, let's call it R naught to be in the same page. Now you will take the value of this R naught that you found from here, then you multiply it by the current source, which is 2 amps, then you will have the V naught in units of volts. You see how fast I solved it? And only manipulation of the circuit. I didn't have to find two equations, then use a system of equation. I didn't have to do that. I only have to use manipulation and just think about it, okay? And also sometimes you can do one or two steps of source transformations, then you can start using mesh analysis or node analysis. Why? Because you can, so I can use this method if I have a bigger circuit. If you, for example, if you have 4 nodes and you do one or two steps of source transformation, and then you reduce the number of nodes from 4 to 2 nodes, that means you have two equations to solve. This one is much better. Also, you can use source transformation for this to reduce the number of equations. So the source transformation is very important. You can never say I don't need the source transformation. That's it for tonight, guys. Sorry for taking a long time with you. As always, I put two examples here. If you want to do it, solve them, I will upload, of course, this file. And one last thing, also source transformation is applicable for dependent current sources. For example, if you have a dependent current source, let's say a dependent voltage source with a value of 2 Vx. If it is in series with a resistor with a value of 2 ohms, you do the same thing. Since it is a voltage source, you divide it by the resistor and put it in series. So this current source, you will obtain a voltage source, dependent voltage source, with a value of what? 2 divided by 2, which is 1 Vx. It is still a dependent current source with a parallel 2 ohm resistor. The resistor is not movable, only I deal with the value of the voltage source using Ohm law to change it, okay? And of course, don't delete this Vx because that's why it is a dependent voltage source. Don't delete it, just manipulate it, okay, guys? So that's it for tonight, guys. I hope that you enjoyed the video, and hopefully I will see you in another tutorials. And take care from now. See you guys.